Now we're kind of back to the topic that Chapter 3 really cares about, which is graphing. Okay, 3.3 is going to be about finding relative max and min and finding intervals of increase and decrease. Very concrete. Here's your example. Motivating example. Y is equal to x cubed minus 9x. Let's graph this bad boy. How would you graph this function? Using all your cunning and all your pre-calculus skills. Make a table all.
Pick the derivative.
It's not using a lot of cunning. It's using pre-calculus skills.
Find x-intercepts.
Yeah, we could at least find the x-intercepts. That would be nice to have, right? So maybe we'll factor this guy. Right, and x pulls out. You're left with x squared minus 9. And then you can break it down again. So each one of these gives me an x-intercept. So x equals 0, x equals 3, x equals negative. In fact, I can tell a little bit more than that by the multiplicity. Do you remember what multiplicity was?
It goes passes through, or if it turns back.
Yeah, so the power of these factors, see how this is x to the first, and this is x minus 3 to the first, and x plus 3 to the first? These all have multiplicity 1. And when you have multiplicity 1, you cross right through the axis, right? Even multiplicity, if this were 2, you bounce. Multiplicity 1 is odd, you cross right through. The other thing I need to know is the degree. What's the degree of this?
3.
3.
Positive.
Yeah, it's positive. Right. Degree equals 3, and the leading coefficient is positive. So that tells me that it's a snake shape, right? Starts down here, ends up here. Because it's degree 3, the end behavior is just like x cubed, because it's positive degree. So then I put my zeros on, or my x-intercepts. So I have to hit this guy and cross through, I have to hit this guy and cross through, I have to hit this guy and cross through. So today we're going to figure out how to actually find these points, and how to prove that this is a relative max here, this is a relative min here. And they're not just in the middle. Okay, I mean, you can't say, well, this is 3 and this is 0, so this is 1/2, right? Or 1.5. It doesn't happen. But this is what we knew. Let's talk about what we know, what we recently learned. What's the derivative of y?
3x squared minus 9.
So y prime is equal to 3x squared minus 9. And I can find critical numbers. Right? We talked about critical numbers last time, where the derivative is 0 or undefined. So for the critical numbers here, I would set y prime equal to 0. So I get 3x squared minus 9x equals 0, or 3x squared equals 9, x squared equals 3, x equals plus or minus root 3. to make you a little chart. Because I like charts. I have a critical number at negative root 3 and a critical number at positive root 3. I would like to test what happens to my derivative, right? So this is going to be what happens to y prime in between. So for example, if I plug in 0 to y prime, what happens? And if I plug in negative 2, what happens? And if I plug in 2, what happens? So these are my critical numbers. And I want to know what happens in between. But y prime, okay? I want to focus on y prime.
Opposite to the left.
So if I plug in negative 2 here, I get 3 times 4 minus 9, which is a positive number. So I'm going to notate that by putting a bunch of plus signs. If I plug in 0 here, I get out negative 9, which is a negative number. If I put in 2, I get out positive. What these tests tell me is how the slope of the tangent line behaves. Right? This is saying, I know where the slope of the tangent line is 0. These are the only 2 places it's 0. So then to the left of that, it's got to be either positive or negative. Positive. In the middle, negative. To the right, positive. So how does this compare to this? So negative root 3 is going to be over here. Positive root 3 is going to be over here. When my derivative is positive, the slope of my tangent line is positive. And when the derivative is negative, the slope of my tangent line is negative. What that translates to on f, whenever your derivative is positive, your function has to be going up. Your function is increasing. Which your book uses Rolle's theorem to prove. But I'm just going to say, look at it. The tangent line is positive, it's going up. The tangent line is negative, it's going down. Right? Tangent line is positive slope, you're increasing. Tangent line is negative slope, you're decreasing. Which means that at negative root 3, because I changed from increasing, right, I was going up, and then I started going down, I must have a maximum, a relative maximum. This is the relative maximum. And at positive root 3, because I changed from decreasing back to increasing, I must have a min. So understanding and drawing this chart and then using it to find your maxes and mins and your increasing and decreasing is the point of this section. All we do in this section. This is what's called the first derivative test. The critical numbers of a function tell you where the possible relative max and relative mins are. Now, what do you think happens if on this diagram I get a plus here and then a plus here? What if the sign doesn't change? What if it stays plus all the way through?
You don't have a relative max?
If it stays plus all the way through, then you're increasing here and you're increasing over here. So you don't have a max or a min. Right? So when the sign changes, then you have a max or min. And if it changes from positive to negative, you have a max. And if it changes from negative to positive, you have a min.
How could you have a 0 slope and not change?
So So how can you have a zero slope and not change from increasing to decreasing or decreasing to increasing? Well, here's a function. It's got a zero slope at x equals 0, right? Because the derivative is 3x squared. So when x equals 0, it's got a zero slope. But the tangent line, the slope doesn't change because whether you plug in a negative number or a positive number, this is still positive. And if you compare this to the graph, it has a horizontal tangent line. Here's the graph of x cubed. It's got a horizontal tangent line, but it's not necessarily a max. So just because you get a zero slope does not mean you have a max or a min. You have to test to make sure that your sign changes. So you have to do this first derivative test to make sure you have a sign change. So let me kind of sum this up. First derivative test. So the first derivative test helps you find relative max, relative extreme, I guess I should say, and also increasing, decreasing intervals. So to do the first derivative test, the first thing you want to do is find the critical numbers of your function. Now, you have to be careful here because sometimes you'll have a discontinuity, which technically is not a critical number, but will come into play. So you also want to make note of any discontinuities, like vertical axis. So where the denominator is 0 for your original function. Then you want to test the intervals between the critical numbers. Between and beyond the critical numbers and discontinuities. This test is going to tell you two things. First, if your derivative is positive, so if f prime is positive, your original function is increasing. If f prime is negative, the original function is decreasing. If you happen to get f prime 0 for a whole interval, what do you think that means? If f prime is 0 for an extended amount of x values for an interval, then f is constant. So if you take your derivative and just get the 0 function, and the original one is constant. But this is, I mean, obviously, if you have a constant function, you're going to take the derivative and get 0. So this is insightful. Anyway. So this is one thing, right? Your first derivative test, after you do your derivative and you plug in your test values, this will tell you whether your function is increasing or decreasing. The other thing it'll tell you about relative max and relative min. So if the sign changes, if f prime changes from positive to negative, negative. What do you think that means about f?
Relative max.
Relative max. That's this situation. From positive to negative, so as you go to the right, from positive to negative, this is a relative max. F has relative max. If it's the other way around as you go to the right, if you change from negative to positive, so like this situation, from negative to positive, then you must have had a relative. This procedure can help you find pretty much everything you know about a function. Okay, relative max, relative min, increasing, decreasing. Make sure I know how to do it now. Let me give you some examples. Okay, so for each function, find all relative extrema and determine the intervals on which the function is increasing or decreasing. So polynomial, good old polynomial. X to the fourth minus 6x squared. I want to know what are the relative extrema, where is it increasing and decreasing? How do you answer those questions? First derivative tells you everything. At least as far as relative max and min and increasing and decreasing. So you're going to start here by taking the derivative and finding the critical numbers. What's the derivative? 4x cubed minus 12x. For critical numbers, you have to worry about where the derivative is 0 or undefined. But this guy's never undefined. Okay, so I'm just going to worry about where f prime equals 0. So I have to solve 4x cubed minus 12x equals 0. So probably factor. 4x comes out. Oops. So what are my critical numbers? 0 or plus or minus root 3? Right, because either x equals 0 either x equals 0 or x squared minus 3 equals 0. This is going to give you plus or minus root 3. At this point, you have your critical numbers, and that's good. You want to go back and make sure that you don't have any discontinuities in your original function. Because if you do have a discontinuity, which we will in the next example, you have to put that into your table when you test. But I don't have any discontinuities. This is the nicest function I can ask for. It's a polynomial. So I'm going to ignore the discontinuities part for this example and just focus on my critical numbers. what I need to do in step 2 to figure out what my relative max, what my relative min are, is make the chart I made in the last example. Right, put my critical numbers on the chart, 0, negative root 3, positive root 3, and then test extra values into the derivative. When you do your first derivative test, you always plug into the derivative, not into the original. So here's my critical numbers. What kind of things should I plug in? Yeah, so you need something to the left of negative root 3. So we'll do negative 2. You need something between negative root 3 and 0. Negative 1. Right, root 3 is like 1.7 or something. So 0 and root 3, you can use 1. And then
2.
you can use 2 for the last step, for the last part. And you're plugging all of this into the derivative. F prime of x equals, let's use a factored form here, 4x times x squared minus 3. So let's not work too hard. Negative 2, what do you think? So when you put negative 2 in for x, this guy's going to be negative, but this factor is going to be positive, right? Because it'll be 4 minus 3. So altogether, this region is negative. If you put negative 1 in, this guy's still negative, but when you put negative 1 in for x, you get a negative in the parentheses. When you plug 1 in, this guy's positive, but this guy's negative because 1 squared minus 3 is negative. And when you plug 2 in, you get positive, positive. So now we can answer our questions, which was about relative extrema and decreasing, increasing. Right, the first, as far as the relative extrema go, you need to realize that negative tangent, slope of the tangent line, means your function's going down. Decreasing on this interval. Increasing on this interval. Decreasing on this interval. Increasing on this interval. So here you're going to have a min. At 0, you're going to have a max. And at root 3, you're going to have since it asks for the relative extrema, I want xy values. So for my relative max, I know x equals 0, but then I have to actually figure out what y equals by doing what? Plug it into the original. So you plug 0 into the original and you get 0. So my point here is 0, 0. Then I have x equals negative root 3. I have to figure out y. And x equals positive root 3. I have to figure out y. They're going to be the same. It's an even function. So let's do negative root 3 here. Do you know what negative root 3 to the 4th is? 9. It's 9, right? Because it is. Right, because it's root 3 times root 3, which is 3. But then root 3 times root 3 again is 3, so it's 9. So 9 minus 18, right, because root 3 squared is 3. 9 minus 18 will give you negative 9. And you'll get the same thing if you plug in root 3. So this is my relative. One of them. What about for the intervals that I'm increasing on? What intervals is my function increasing on? Remember how to write that?
Open bracket, parentheses, negative root 3 to 0.
Right, so on this interval my function's going up. So for increasing I'll put negative root 3 to 0. And then I have to put my second interval that I'm increasing on.
Root 3 to infinity.
Because it goes on forever, you're going to use infinity.
Can you put the little union guy? Or
I wouldn't say it's technically correct in this case. Because you're increasing here and you're increasing here, but you're not necessarily increasing from here to here. Like if I pick a point here and I pick a point here, this point could be lower. For example. I give you something like. So like increasing says that you're always going up as you move left to right. So if you put a union, that would be saying that from here to here, you've increased. But you haven't because you stopped increasing here. So because you actually stop increasing and the increasing is confined just to that interval, it's not technically correct to put a union. I don't technically care. And then decreasing would be the other. The other intervals. Decreasing is when you're negative, when your derivative is negative. So negative infinity to negative root 3. Zero to root 3. That's cool. How cool is that? That's very cool. Right? We took this function, no idea what it looks like. We can come up with an idea, but we have no idea what it looks like. And we figured out where the relative max, relative min are, where it's increasing, decreasing. We get a good picture of this. I'm not gonna, because that's for 3/6, but. But you don't care, so whatever. I'll just be happy. I'll be happy for the function. So questions before I give you one more. So you have to be a little careful when you have denominators. Here's another function. I want the relative max, relative min, increasing, decreasing. When I'm supposed to find the relative max and relative min, what do? Find critical numbers, right? Take derivatives at equals 0 or undefined. That's one. Critical numbers. So I take g of x, which is equal to, let me go ahead and write it with a negative exponent. Right, g of x is x minus 4 to the negative 3. Then I do the derivative. So g prime of x will be equal to negative 3, x minus 4 to the negative 4. And then you would multiply by the derivative of the inside, but what's the derivative of the inside? Just 1, so I'll not worry. So g prime of x equals negative 3 over x minus 4. 4. So what happens here? Is g prime ever 0? No, right? Because the numerator is never 0. Is g prime undefined?
X equals 4.
Yeah. Now here you have to be a little careful because x equals 4 is actually not in the domain of the original function. So technically speaking, I'm getting in a lot of technicalities, I guess. This is not a critical number. But what happens at x equals 4? If you look at the original function, what happens when you have a 0 denominator?
It's vertical axis.
It's a vertical axis. So you still want to consider it in your tests, but it's not technically critical. So what happens here when we do our tests? We make our number line. And I'm still going to put 4 here. Now I want to test each side of 4, so I'll do 3 and 5. And what do I test them into? So here's the derivative. So what happens when I plug in 3?
-3.
You get a negative number, right? If you plug 3 in here, 3 minus 1, or 3 minus 4 is negative 1, but you're taking it to the 4th power. The bottom's always positive. The top's always negative. So when I plug in 5, I'm going to get the same thing. So what's that tell me?
You don't have
Relative max, relative min. Are there any?
no.
None. Right, the only possible place where you could have a relative max or min is actually a vertical asymptote. What about increasing? Is my function ever increasing? No. It's always going down. So the only thing I can fill out here is decreasing. When is my function decreasing?
Infinity.
So negative infinity to 4,
Union.
it's decreasing on that interval, and then after that it's decreasing again.
Now you can actually put your. No?
Now, do you guys know what this? Do you guys know what this function looks like?
Oh, okay, never mind.
1 over x squared.
So 1, 2, 3, 4. It's going down like this here, and it's going down like this over here. So it kind of jumps back up. So it's technically not decreasing over the whole real line because, or over these two intervals because it jumps up right here. But these are my three answers. I don't want to do a whole bunch of them. But I do want to see what happens here if I change this exponent. Better marker. Yay. What happens if I change this to h of x equals 1 over x minus 4 squared? What does that do over here? h of x is x minus 4 to the negative 2, so h prime of x is negative 2x minus 4 to the negative 3. Or h prime of x is equal to negative 2 over x minus 4 cubed. So then when I search for my critical numbers, what do I get? X equals 4 again is a discontinuity. It's another vertical asymptote. So I still have an x equals 4 problem. But what are my tests going to show?
Positive and negative.
Yeah, so now my tests are going to flip. I have 4. If you plug in something to the left of 4, like 3, this will be negative on the bottom and negative on the top, so positive. If you plug in something to the right of 4, like 5, positive on the bottom, negative on the top. So I do actually flip here on this one. But this is where you got to be careful, because you might think, right? You might think for this function, because I'm going up here and I'm going down here, that I have a relative max at 4. Do I have a relative max at 4?
We don't.
It's an asymptote. You can't have a relative max there. The function's not defined there. Vertical asymptote. So there's still no relative max or min, because our only possibility was an asymptote. And then now we have increased book, but we happen to have increasing and decreasing intervals. Increasing negative infinity to 4, decreasing 4 to 4. So my point with these two functions is, if you have a discontinuity, you have to include it in the test no matter what. But that discontinuity will never be a relative extrema. It'll be an asymptote. One more. X plus sine x. Just do it on the interval 0 to 2 pi. So I want to know all relative extrema and where it's increasing and decreasing. So to find relative extrema, I need critical numbers. So how do I get the critical numbers of this bad boy? Take the derivative.
Always a good idea.
Oh, it's a good idea. Take some derivatives. So f is x plus sine x. F prime is 1 plus cos x. So this is always defined, which means I never have to worry about undefined for critical numbers, but I do have to worry about 0. So I solve 1 plus cos x equals 0, which gives me cos x equals negative 1. And because I only care about the interval 0 to 2 pi, I should only get one answer to this. Yeah. So in order for cosine to be negative 1, you have to be over here. And that's pi. So when I test, careful, you don't want to go too far, because I want everything to stay on 0 to 2 pi. So if you're going to plug things in, you don't want to plug in like negative 1,000 pi or something ridiculous. Let's try pi over 2 and 3 pi over 2. Right, those are really nice because they're on the y-axis. And you always want to plug into the derivative when you're doing your first derivative test. Right? This is a chart for f prime. Okay? So when I plug in pi over 2, what do I get out of f prime? Which is positive or negative? Positive. When I plug in 3 pi over 2, what do I get out of f prime?
1. Oh, 1.
1. Right? If I plug in 3 pi over 2, this is 0 again. So again, I'm getting a situation where I haven't changed from positive to negative. So as far as relative extrema go, what do I have? None. Increasing?
Always.
Always. In this case, because there's not a discontinuity here, right, there's no break in the graph here, this is actually increasing on the entire interval, 0 to 2 pi. But you could write 0 to pi, and then 0 to pi, and then pi to 2 pi. Yeah. This is more correct. You always do open intervals for increase and decrease. So this is what happened. So this graph is kind of cool. You ever seen the graph of x plus sine x? It's like you take x, y equals x, but then you add sine to it. So it takes that shape and just wiggles up. But it's always going up. It looks like this. It's always increasing.
Interesting.
Anywho, all right, I will be done.